je vais parler en anglais. Je suis désolé, mais j'ai peur. C'est aussi simple que ça. I didn't speak French for many years, and it would be horrible. So, c'est quoi la... Yeah, what, you see, I don't even know the gender of proof. So what is proof? So that's what we're going to talk about. What does the word proof mean in practice to people like me? What does the word proof mean to a computer? And maybe we can we bring these two together later on? So it's an ambiguous word, the word proof. Physicists use it. They proved the existence of the Higgs boson, and this has a rigorous definition. This has to be, it has to be 5 sigma significance. So that's what a proof is to a physicist. But of course, I'm a mathematician, and so I can beat the physicists because I can prove this with 100% certainty. Because I'm not operating in the physical universe, I'm operating in a mathematical universe where things are true and false, and one can decide these things. So I'm going to talk about the idea of mathematical proof, and you would imagine that this idea, 5 years ago, I personally imagined that there was no issue here at all, really. I know exactly what a proof is, and it's, there are well-defined rules, and an argument is either correct or it's incorrect, and the important stuff gets published in prestigious journals. So that's how we know if something's been proved or not. Fortunately, you see, we don't have to read it as long as it's been published in a prestigious journal. We know it must be true. Because, we have checks and balances. That's how it works. So here's what they don't tell us, and that's what actually happens in practice. So I'm going to start with some case studies, and I'm going to start with my favorite one, which is what happens when we prove contradictory things. So when somebody proves X and somebody else proves Y, and if you put X and Y together, there's some problem. So can this happen? So yes, it can, unfortunately. And here's a completely explicit example. The first paper was published in the Annals of Mathematics. So this is the most, where I'm sitting at least, this is the most prestigious pure mathematics journal. And some technical theorem is proved, but basically they prove that moduli spaces are quasi-projective. So this was proved in 2004. And then in 2006, somebody else proves that moduli spaces are not all quasi-projective. And this is also published in the Annals of Mathematics. So this is big news, right, in the mathematics community, because now we have a proof that something is true and a proof that something is false. And so now you can prove everything is true and everything is false. And this fact was even highlighted in the abstract. You see, the author thought that this was very important to stress, that there's now a contradiction in mathematics. And so either mathematics is broken or one of these papers is incorrect, right? And if mathematics got broken in 2006, we would know about it now. So you can see that actually what must be happening is that one of these two papers is incorrect. So which one is incorrect? Unfortunately, that's a secret. You can't find out which one is incorrect unless you pay. And if you pay, you can discover, because the experts know where the problems are. And the American Math Society run a website called Math Reviews, where they write reviews of papers. And if you read the reviews of these two papers, it will become very clear which one is the correct paper and which one is the incorrect paper. But you have to pay to see that information. And the Annals of Mathematics, they must know, right? But neither paper has been retracted. There's no commentary on the Annals of Mathematics website saying, oh, by the way, the main theorem in this paper is incorrect. That's nowhere on the Annals of Mathematics website. So maybe one day I will get around to doing this. Just, send a one-page proof of the Riemann hypothesis to the Annals of Mathematics and just deduce it from these two papers. But I didn't do it yet. If I'm feeling more mischievous, maybe I'll get around to it. So that's kind of, that's strange, because that's not how you really expect mathematics to work. Maybe it's slightly unprofessional, I don't know. I should say the last time I looked, all these three authors, had their Annals of Mathematics papers proudly displayed on their websites. In fact, I should say something else as well. One of these papers is incorrect, but it also contains a lot of brilliant arguments which are very useful for other applications. So who cares that it's wrong? It was useful anyway. So that's a strange thing. Here's another strange thing. There was an open problem in number theory. It looks like a very strange, unmotivated question, but for some reason, number theorists were very interested in finding all the rational numbers x and y, which satisfied this random degree 4 equation. And the reason that they were interested was because this random degree 4 equation happens to be the equation which defines a parameter space, a moduli space of elliptic curves. So if you find a solution to this equation, you found an elliptic curve with some property. And people wanted to know all the elliptic curves with this property. So solving equations like this in rational numbers is very hard. And this equation was particularly interesting because the techniques we knew up until about 5 years ago were not sufficient to solve this equation. But new techniques developed by people like Min-Hyung Kim. Several of the authors of this were students of Min-Hyung. Somehow, Min-Hyung Kim developed some machinery which enabled these young folk to finally resolve this equation. We have a complete list of the solutions to this equation. As I say, this is not just a random degree 4 equation. They said solving this equation had consequences. For example, it gave us a new proof of the class number 1 formula for imaginary quadratic fields. And it was also published in the Annals of Mathematics, so the most prestigious pure mathematics journal. But this time the proof isn't wrong, but this time the proof is just secret. Or part of the proof is secret, because they use a computer to do some of the calculations. There's a key point in the middle where they need to verify a lot of things, and they type it into a computer, and they get the computer to check. The computer has to just do a lot of work, and it does it quietly, and then it announces that that the work is finished and nothing weird happened. And you can run the program as many times as you like, and it will always say the same thing. So the program they used was this thing called Magma. So this is a computer algebra software that you have to buy, and it's closed source. So you can't see the source code to Magma. You don't really know what it's doing. But one of the reasons that the University of Sydney can sell Magma is because it's very, very fast, because they've generated, they have good techniques for taking quotients of abelian groups by subgroups. And these good techniques are techniques that they've developed internally and have not published, because if they publish them, then the other computer algebra packages could use them as well, right? So they keep them secret. These are unverified algorithms, unrefereed algorithms, and you can't see what they're doing. You can only see the answers. And these algorithms are being used to do these calculations, which are essential for the proof of this theorem. So part of the proof is secret. And I asked Jennifer Balakrishnan how the refereeing process actually happened. And she told me that actually they made all the code available and said they would answer questions about it, but none of the referees asked any questions about the code. And so I asked her whether it would be possible to do the same thing in an open source system, and she said yes, but you would have to write a lot of code, and it would run much more slowly because they don't have access to the fast algorithms, the fast secret algorithms of Magma. So it could, in theory, be done, and then the proof wouldn't be secret anymore. But nobody's going to do that because why would you do that? Right? Nobody cares. Part of the proof is secret, but the proof is accepted by the community. This is the crucial thing. We, as a community of number theorists, are very happy to believe that, asking Magma to do some of the calculations is a valid method of proof, even though it results in part of the argument being secret. So that's funny. What's the next story? I guess this is a slightly sad story. This well-known theorem of the classification of finite simple groups. Well, it's not sad yet, but it is uncomfortable. So the proof was announced in the 1980s. This was the big conjecture in finite group theory. Classifying the finite simple groups is like working out the periodic table in chemistry. It's of fundamental importance. The periodic table tells us the complete list of atoms that everything is made from. So this is the analogous result in group theory. Every finite group is made by gluing together finite simple groups. And so you want to work out what all the finite simple groups are. So the proof was thousands of pages long. And maybe all of it is in the literature somewhere, if you know where to look. But what group theorists are attempting to do is to write down a big collection of 11 volumes of mathematics where the full proof is written down. And things are going slowly, but they haven't stopped yet. But a lot of the people involved are very old and have retired, and you can't really imagine that this is the most important thing in their life. But on the other hand, if these people don't do it, then things will go backwards, right? If some random people, die of COVID, then this would probably be quite inconvenient when it comes. This proof could die. It probably won't, but in theory it could, because somehow it wasn't written when it should have been written, and it's kind of big and unwieldy. And of course, the other problem is that when you solve the biggest conjecture in the area, then all of a sudden, it's not so clear what the direction of the area is anymore. And so maybe many young people will not go into the area. So, or the moment an area loses its biggest conjecture, there's a chance that the area might begin to die. And then when the experts have died out 50 years later, there's a chance that there's problems. So, there's a proof. Maybe it will survive. I think it will. These people are still writing these volumes. There's got 2 more to go, and then they're done. So let's hope it happens. But in some sense, it also represents a failure of the system. So what's next? The ABC conjecture. So this is very problematic because it's a famous unsolved problem in number theory, and a proof is now published, right? And that's how you know that's the general community consensus is that if something gets published in a reasonable journal, and this is a perfectly good journal, then then it means that the community has accepted the proof. But the community has not accepted this proof, even though it's now published in a reputable journal. Right now, there's still a lot of people that think this proof is incomplete. They think that something is missing. Maybe it can become a proof. I don't know, but right now the proof is incomplete. And if you look on the Wikipedia, there were sort of edit wars for a while. But now if you look on the Wikipedia page, at least the English Wikipedia page, one should look at the French Wikipedia page. I don't know what it says. What is it? Oh, the Japanese Wikipedia page would be another very good one to look at. Right now, the English Wikipedia page says that the ABC conjecture is not proved, and that there was a failed attempt to prove it by Mochizuki. But the difference is the papers have been published, right? This is a crucial thing. The papers are published in a reasonable mathematical journal. And so, and if now that is no longer the test, if that's no longer the test to see if the community accepts the proof, then this is problematic, right? So obviously, what's the thing to do? I should read the proof myself, right? And decide whether the theorem is proved or not. I'm a number theorist, after all. So why don't I just read all the papers? And it's hundreds of pages long, and I don't want to do that. Because what if I read it and then I decide that I can't make any sense of it? Then I've wasted a lot of time learning a useless theory. So I'm not going to read it, and now we're kind of stuck. Because it's out there, and some people believe it, and many people don't believe it, and that's the end. And Mochizuki is writing more, right? There are more papers come out where they prove more stuff. I think they're going to prove Fermat's last theorem next. They're going to give a new proof of Fermat's last theorem. And who knows? I don't know. So mathematicians and proof have a kind of a complicated relationship. So that's humans and proof. So now let me talk about something more formal. What's a formal definition of a proof? So it turns out that we do know this as well, right? About 100 years ago, we started, things like Russell's paradox were appearing, and mathematicians had to decide what mathematics is valid. What are you allowed to do with mathematical objects? And people had to start writing down the rules of mathematics. So even though we've been doing mathematics for thousands of years, it was only around 100 years ago that it became very clear that we need to actually decide what mathematics was. So we wrote down some axioms, and we announced that these seemed to work in the sense that we wrote down the axioms, and then we verified that everything that had happened before then was valid mathematics. And on the way, of course, we had to say what a proof was. So mathematicians do know what a proof is. Somehow those earlier examples were mathematicians in some sense having different opinions about what a proof was, but the formal definition we're all agreed with, and it's something like this. It's quite a boring definition. It's just a list of statements written in some formal language, which can be completely specified. So every statement has to make sense. And every statement either has to be an axiom of mathematics or something you can deduce from the axioms of mathematics. So there you go. So that's what a proof, that's the answer. That's what a proof is. It's that, right? And so here's some examples of, one of the axioms of mathematics is that a set exists. And one of the rules of logic we're allowed is that if P is true and P implies Q, then Q is true. So you can see the axioms of mathematics and the rules of classical logic are somehow very fundamental, primitive things, and somehow a very long way away from how mathematicians actually think in practice. But there you go, it's a definition. And of course, the advantages of having a proper definition is that for a start, you can now attempt to say this is a proof, this is definitely a proof, this is definitely not a proof. You can say things like that. But then secondly, you can teach a computer what a proof is. Because computers, once you've broken everything down to logic, I mean, this is exactly what computers are very good at. They're very logical. They're very logical things. So let me give you a very simple mathematical proof, and it's the proof that the composite of two injective functions is injective. So we've got x and y and z as sets, and we've got a function f from x to y, and a function g from y to z. And I claim, this is the kind of thing I teach my first-year undergraduates, I claim that if these two functions, f and g, are both injective functions, one-to-one functions, so they take different elements of the source to different elements of the target. If f and g are both injective, then so is their composition, g composed with f, g of f. G of f goes from x to z. You do f and then you do g. And this is the claim. If f and g are injective, then so is their composition. And I'll give you the proof, right? All I'm going to use is sort of the definition of injective and the rules of logic. So here's the proof. What is it? I'm trying to prove that this is injective. So I need to take two elements of x, and I need to assume that they're the same when you send them over to z. And then the question is, were they already the same in x? So that's what we have to do. That's just rewriting the definition of injectivity. And now, traditionally, mathematicians argue by taking their assumptions and manipulating them until they become equal to the goal. But for reasons that I'm not going to explain, I'm going to start with the goal, and I'm going to manipulate it until it becomes an assumption. So I'm going to write the proof backwards in some sense. So we're trying to prove we have x1 and x2, two elements of capital X, and I want to prove that x1 equals x2. And the first thing I'm going to say is, well, but we have f, right? F is an injective function. And so that means that if f of x1 equals f of x2, then x1 equals x2. That follows from injectivity of f. So we're trying to prove x1 equals x2. And injectivity of f tells us that if f of x1 equals f of x2, then x1 equals x2. So all we have to do is prove that f of x1 equals f of x2. Right? If we've done that, then we're finished. And then similarly, injectivity of g tells us if we prove gfx1 is gfx2, then we can deduce fx1 equals x2. Sorry, we can deduce fx1 equals fx2. So we can deduce what we want if we can prove this more complicated thing, gfx1 equals gfx2. So now we have to prove this complicated thing, gfx1 equals gfx2, but that was exactly what we assumed, you see. So that's our assumption. So there's a proof from first principles, right? It's somehow all I did, I took very slow and simple steps, and that's what I tell the undergraduates that a proof is, you see. So I live this lie, right? I write mathematical papers where I operate at some level high above the axioms, but then I tell the undergraduates that proofs have to look like this. So there's a mathematical proof, and it turns out that if you ask a computer scientist what a proof is, it turns out that they have this completely different way of thinking about it, that they say a proof is a computer program, or a proof is a function, something like this. And it's even got some fancy name, the Curry-Howard correspondence. So a proof is a function, which means that I mean, f and g are functions for sure, but apparently this proof is also a function in some strange way. So next thing I'm going to do is I'm going to show you how to make that proof into a function. So I'm now going to use a computer theorem prover. Do you know what? Before I do that,
let's do this. Let's go back. Let's take here's my proof here. Let's just cut and paste it like this. And here we go. Let's dump it there. There we go. So this is let's go. Mm-hmm. This is a computer theorem prover. And right now, it has lots of errors. There's this error count down the bottom. There you go. Right now, we have 9 errors in our program. So what's going on? X and Y and Z are sets. I mean, I've called them types because this particular theorem prover uses type theory instead of set theory. But a set is a collection of elements, and a type is a collection of terms. So they're the same thing, really. So X, Y, and Z are sets. And I've got a function from X to Y and a function from Y to Z. And then here's the theorem we're going to prove, right? We're going to prove that if F is injective and if G is injective, then G composed with F is injective. So it's the same thing. And here is the human proof that I just cut and paste. I just cut and pasted it from my slides, and it doesn't compile. And that's because computers don't understand human language. So you see, assume we have an error. I mean, we could look at the errors, right? There we go. All the errors will just say, you see, it's like, it just says, I don't understand what these words mean. So we have to rewrite the proof. The problem is this is a proof written in a human language, and we need to rewrite it in a computer language. So let me comment this proof out there. And now let me apologize. Sorry. And there. Sorry means I didn't prove this yet. Great, so now I'm down to 0 errors, but I have one warning, and the warning is that I cheated because sorry means I give up. So right now, where are we at the start? Here we go. So this is a computer theorem prover, and this is the current state of its brain at this point. It has 3 sets, X, Y, and Z. It has functions from X to Y and from Y to Z. These are the hypotheses. It has the hypotheses that F is injective and that G is injective. And then we have this strange sideways T that probably has a name in computer science, but I don't know what it is. But after that thing is the thing you're supposed to be proving. I do know that. So we're supposed to be proving that G composed with F is injective, and the hypotheses are all those other things above it. And so now what we have to do is we have to figure out how to translate this human proof into a computer proof. And so I can do this because I know how to speak this computer language. So for example, this first line here, assume that x1 and x2 are in X. So that's intros x1, x2, and H. So that's how to translate that first, that's the translation of that first line into this computer, into the language of Lean. And now you can see what's happened on the right here. Things have changed, right? We've got new stuff that wasn't there before. Little x1 and little x2 are elements of the set capital X. And we have a new hypothesis, H. I'll pull it out a bit. There. We have a new hypothesis, H, that says GFX1 is GFX2. And our goal now, you see, I can move the cursor up. You see, the goal used to be prove that G composed with F is injective, and now it's something else. In fact, that's what it says in our proof. Right? Our goal is to prove x1 equals x2. You see, we don't need to translate that at all. The computer knows exactly what the goal is, right? The goal changed, but the computer figured it out. So what's the next line? Injectivity of F tells us that fx1 is fx2 implies x1 is x2. So it suffices to prove that fx1 is fx2. So we're using injectivity of F, and that has a name. That's HF. So let me apply HF. There we go. And now the goal has changed again. The goal, if I go up with the cursor, the goal used to be to prove that x1 equals x2, and now it's to prove that fx1 is fx2. And now what's the next line of the human proof? Injectivity of G tells us this, so it suffices to prove this. So I guess I can just apply HG there. And now our goal is to prove that GFX1 is GFX2. And that's exactly hypothesis H. Actually, you look at it now and you see it's not exactly hypothesis H because hypothesis H has got function composition in. But the definition of function composition, the definition of g f x1 is g of f of x1. And so, in fact, this goal here is exactly this hypothesis here, at least up to definitional equality, which is the kind of thing you have to learn about if you want to learn how to use theorem provers. So I claim that the goal is, in fact, exactly equal to this hypothesis H. So let's see if the computer believes us. Exact H. There you go, it did. Great. So now the computer says we're finished, right? Yeah, it's completely different on the right-hand side here, because it used to say what the problem was. We were playing a computer game, right? And we used to be able to see what the status of the game was. You know, that was the situation where we were. But now, you know, the game is over, and you can tell it's over because we have a total score of 0, which means we won. Right? We have no warnings, and we have no errors. And so we've won the computer game, and we've proved the theorem that the composite of two injective functions was injective. So now I'm going to prove it again. Let's prove it down here. But now I'm going to prove it by making a function, because a proof is a function. So this is. There we go. So for me, it's quite surprising that a proof is a function. But what's going on here is our goal is to prove that G composed with F is injective. And so our goal is to create a function that does the following things. Firstly, the function takes an element of x, call it x1, and then it takes another element of x, call it x2, and then it takes as input a proof that gfx1 equals gfx2, and then the output of the function is another proof, and it's the proof that x1 equals x2, right? That's why a proof is a function. So I need to construct a function. So normally mathematicians think of functions as eating things like numbers, but computer proof systems, they can't tell the difference between numbers and proofs. They'll quite happily take a proof as an input. So let's write this function, and this is a functional programming language, so I'm going to use lambdas, right? I'm going to use lambda x1, x2, h, comma something. So I haven't finished writing the function yet, but this is a function that takes three inputs, x1, x2, and h, and then it's got to output something, and I don't know what its output. You see, I've got an error again, you see. I've got an unfinished proof, or an undefined, I've got a partially defined function, so Lean is complaining that the system doesn't compile. But you can see what we need over here. We've got x1 and x2 and this hypothesis h, and Lean is expecting us to output a proof that x1 equals x2. And we can look at where that proof came from, right? First, we use HF, right? HF is a hypothesis that f is injective, but HF is also a function. HF is a function that takes the proof that fx1 equals fx2, and it outputs a proof that x1 equals x2. That's what HF does. So we can apply that. It's HF of something, right? There. F is a function, HF is also a function. So it's HF of something, and the input to HF needs to be a proof that fx1 equals fx2, and we can just get that from hg, right? hg of something. And now, you see, so we're slowly building this function, and now hg needs as input a proof that gfx1 is gfx2, so it just needs h. So there we go. So let's put h here, there, and now everything is compiled again. So again, I've got no warnings and no errors. And I've got what looks like if you've never seen a functional programming language, then this looks like a very strange line of computer code. But this line of computer code is a genuine, absolute, bona fide, 100% proof that the composite of two injective functions is injective. And that's how a computer proof system sort of internally stores that proof. And I think that's quite strange and rather beautiful. So that's why a proof is a function. Now let's do this. There we are. So, of course, the big problem with the formal definition is that, I only think about mathematics in that axiomatic way when I'm teaching the undergraduates. Right? When I'm doing my research, I don't think about there exists a set and stuff like that. I don't think about axioms like that at all. In fact, let me show you a picture from this Piccirillo paper. This is a recent paper, again published in the Annals, that proved a theorem in knot theory, proved that the Conway knot was not slice. And this is my favourite picture, my favourite page of the paper, where she just draws a whole bunch of pictures and then says, and claims that this is a proof of a theorem. In fact, there's J, K, and L on the next page as well. The proof is 12 pictures long, and it involves manipulating. This is a theorem about knots, right? This isn't some weird representation of something else. This is a piece of string on a table, and she's proving a very delicate theorem about a certain kind of knot. And you just saw how a computer proof system thinks about mathematics, and now we're faced with the problem that this is clearly valid mathematics. This isn't a problematic proof. This is the kind of proof which is completely acceptable in the topology and knot theory community. And yet, how am I, as a formalizer, expected to translate those pictures into the kind of thing that my computer theorem prover can understand? Right? Because, we say we're operating, we claim that everything follows from the axioms, but here something different is happening, and it would be possible, but it would be extremely hard work to change that proof into an axiomatic proof in the sense of the lean theorem prover. So let me stress, unlike some of the earlier things, there's no problem with Piccirillo's proof. It's just there's some kind of culture clash. So let me mention Silvia Di Toffoli. She's a philosopher at Princeton, but she's got a PhD in topology. She's got a PhD in mathematics and has now become a philosopher of mathematics. And I'm a big fan of her work because she's got a PhD. She knows what mathematics is about. So she's trying to reconcile these two ideas that a proof is something which follows from the axioms and compared to what we're seeing in the literature. And she came up with this definition this year, a simul proof. And it's kind of long, but let me kind of read it. An argument is a simul proof when it's shareable. That means that what you've written is readable by other people. So experts can read your work, and then some agents, these agents can't be random humans. I think they should be probably, experts in your area. Some experts in your area have claimed that all the parts are correct. So some people are accepting it as a proof, and furthermore, the paper looks like it's not crazy somehow. This is her attempt, and I think it's a very good attempt, to summarize what's actually happening in the mathematical literature, in contrast, to this rigorous definition of proof that we have. And she points out that, a proof is not a simul proof, and a simul proof is not a proof, because there are examples of simul proofs in the literature which turn out to be false, but they were, accepted by the community anyway. So there's a nice working definition of what mathematicians are actually doing. We're producing simul proofs. And as I say, without computer assistance, because I should, in case it wasn't clear, that computer theorem prover business, this stuff here, this is how I actually do my mathematics now, but this is not how the mathematical community in general does mathematics, right? This is a relatively new development somehow. I mean, 5 years ago, it wasn't how I was doing mathematics. So most humans do not use these theorem provers, and so if you don't use theorem provers, then that's as far as we can get, because humans are fallible, basically. This is in the title of Sylvia's paper, a fallibilist account of mathematics. So, of course, what you see, what we see in the simul proofs which are being published in the literature, things like this, this is fine, this follows from Theorem 37 of paper X, but when they say, things like this is, more troublesome, this follows from the techniques that are used to prove Theorem 37, because that means that you have to now go and read the proof somehow. You can't just read the statement, you have to read the proof as well. Or sometimes people are even worse, right? They just assume that you're an expert in the area. So they just say, well, this is all, as long as you know the theory developed in paper X, everything's easy. So this is the kind of things you see in these simul proofs that we're generating. And why do mathematicians write like this? Is it because we're lazy or incompetent or ignorant? I mean, the truth is that it's none of those things. The truth is that we don't like the axioms in particular. We did mathematics for thousands of years without any axioms at all. And what's really going on is that as mathematicians, we see beauty in mathematics, like many people see beauty in things like art and music. And complex mathematical ideas can be very beautiful to us. But unfortunately, to see the beauty, I think it's necessary to step a long way back from the axioms, in the same way that if you're trying to appreciate some work of art by Monet, then you don't just walk right up to it and look very carefully and observe the type of paint which was used somehow. Or if you're listening to some musical track, you don't run it through some, you don't break it down into sine waves and write down the frequencies, or you don't stare very hard at the guitar and the drum that made the music. You somehow need to appreciate it in a different way. You're not thinking about how it was constructed, you're thinking about it as a whole. So we appreciate mathematics in a highly non-axiomatic way, and that's where the beauty is. And so we don't write in an axiomatic way because it would be boring somehow. And the job maybe of an author is to convey the beauty of what they've discovered to the reader, right? They're telling a story. And they don't really want to get bogged down with the mechanics of how it all worked. And so this is the problem that an author is then faced with. They have to decide how to tell the story. And so the author has to make these decisions, right? Firstly, they have to decide where they're going to start. And secondly, they have to decide how fast they're going to go, right? The initial conditions, right? What's the initial position, and what's the velocity that we're going to go through this proof at? And if the author starts too far ahead of you or moves too quickly for you, then you cannot read the paper. But that doesn't mean that the paper has failed. It just means you weren't the intended audience, which is problematic, right? If you're a PhD student trying to learn an area, then you have to find the right papers to read because you're not ready for many of the papers. So those are problems which an author has. And as I say, then the author takes the reader on a journey, and the point is the reader has to start at the same place as the author, and then the reader has to keep up. So this is the end. Currently, as I say, the author of a proof has to make some big decisions about how to write their paper. And I think we're getting to the point now where there will be other ways of doing it. And in particular, maybe in a few years, we're going to have a workable system where, in theory, a mathematician would be able to write papers where the reader can decide how fast they're going to go and where they're going to start. Because all the information will be there, right down to the axioms of mathematics. But it won't be it won't be right there on the front page, right? It needs to be there but hidden. That's the problem. Because if it's there but not hidden, then your paper is 200 pages long and extremely boring. And if it's not there at all, then your paper is not readable by beginners. So it needs to be there but hidden somehow. And computers are going to be good at this, right? So let me finish by showing you a project which I've been involved with, which is probably here. No, it's maybe here then, yeah. So this is research level mathematics. In fact, it's mathematics written by Peter Scholzer and Dustin Clausen. It's part of a formalized proof of a theorem they proved. And this is just written in LaTeX. This was written by humans in LaTeX, but this stuff is powered by the computer proof system we saw earlier. So that's a genuine URL for it. It's just that I have no internet right now, but I don't need internet. And the idea is humans can read this stuff, but if they want to see more detail, they can start poking around here, and I guess what's going to work? There we go. So, for example, you see the proof is omitted, right? This proof is deemed too simple to bother humans with. But what if you're just some beginner and you can't understand anything and you don't know what a profinitely filtered pseudo-normed group is? Then maybe it would be helpful to read the proof. But the proof is there. It's just that we can't see it right now. Where is the proof? I guess there. The proof is here. This is a link. If I had internet, I could click here and jump to this link. But I guess I can just. So this proof is called eval fp comp. So maybe I can just go to here and search for. Oh, there we go. That must have been rehearsal. Eval fp comp. I've done it already, and we can click here. And there we can see, so there we go. So this is the hidden proof, but of course the problem is the beginner still knows nothing because this is written in an incomprehensible computer language. I mean, except if they're someone like me, because I can read it, right? I invested 6 months of my life learning what this language said and how it worked. And now now I can look at the proof, right? And the proof says, just do things which mathematicians find trivial, apart from this one thing here. So there's one lemma which is being used, and everything else is noise. So there we go. And so we can look at the statement of this lemma as well, I guess. There we go. We can jump here. And there's a lemma. You see, right now it's not finished, right? This is of no use at all to humans. But when we finished it and put kind of documentation that explains what's going on and put comments in here that say what's actually happening, then we'll have some kind of system where you can zoom in as much as you like, but if you're not interested, then you can keep going. So this software is very primitive at the minute in some sense, but it's certainly capable of doing research-level mathematics. And so somehow it's only a matter of time before people start putting everything together and we see systems where there's some new kind of web-based papers, which will be nice to see. So there you go. Will mathematics, Will it all look like this in the future? I mean, probably not, because we can't persuade, it's difficult to persuade people to change. And also, whether or not this kind of mathematics, doing mathematics in a theorem prover, whether this is the kind of thing that the mathematical community is prepared to support, that's also another very complex question. But at the end of the day, I do feel that humans think about mathematics in a different way to the way computers do. Humans come up with the brilliant ideas, and computers check all the boring parts. And so I wonder whether we should somehow separate these out and start collaborating with computers instead. So that's it. Thank you very much.